A computer program executing in total isolation is perfectly safe. It is entirely predictable, and practically speaking, it is completely useless. To actually generate value, that isolated system has to cross its own boundaries. It has to reach out to the external world to pull in data or push out a result. But the precise moment a program attempts to read a file or ask a user for input, it sacrifices that perfect isolation. It exposes itself to an environment that is chaotic, unpredictable, and unstable. Robust engineering requires both sound internal logic and the mechanisms to safely bridge the gap to the outside world. When your program accesses external data, it faces two primary threats. First, it can leave system resources permanently locked open. Second, it can encounter unexpected data that triggers a fatal runtime anomaly. Mitigating these threats requires a rigid structural defense system. We are going to deconstruct Python's architecture for safe execution. We'll map the exact life cycle of file input and output, and trace the control flows required to intercept system failures before they bring the whole process down. Standard educational materials for Python highlight this doctrine. Always close files and handle exceptions to avoid crashes. These patterns provide the structural foundation for system stability. Interacting with an external file relies on a strict life cycle of resource allocation. You initialize the connection, perform an operation, and then release the resource. The manual approach uses open to claim a file as a system resource, while R locks it into a read-only state. Next, the system ingests raw data via file.read. Finally, file.close unlocks the resource, freeing memory. But there is a hidden vulnerability in this sequence. If the program encounters an error during the read phase and suddenly halts, it never reaches that manual close command. The system resource remains locked open indefinitely, creating a memory leak. Relying entirely on manual memory management assumes perfect, uninterrupted execution, a condition rarely met in real-world environments. Python provides a specific architectural solution designed to eliminate the vulnerability of manual resource release. This alternative approach encapsulates the input-output operation. The with keyword initializes a context manager, automatically handling the setup and teardown lifecycle. The exact millisecond the indented block finishes, the resource is closed, even if an error occurs. The with statement transforms a manual, error-prone task into a reliable, automated process. Securing the file resource is only half the battle. Even with a context manager working perfectly, the actual data inside that external file remains entirely unpredictable. You might request a specific document only to trigger a file not found error. Or your program might expect to ingest numerical data, but receives raw text instead, throwing a value error. In Python, an unhandled exception acts like a severe biological shock. It results in the immediate termination of all program functions. A single unhandled anomaly forcefully stops an otherwise healthy execution pipeline. Everything shatters completely, and the system immediately freezes. Building software on the assumption that external data will always look perfect is a fatal flaw. A robust system must be designed to absorb and neutralize bad data before it causes a crash. This is where we implement a control flow interceptor. This is a logic structure designed specifically to catch failure states before they trigger a full system collapse. This flowchart outlines the interceptor pattern. It begins with the try block, acting as a protective quarantine zone for dangerous operations. Below is the except block, the active defense layer that reroutes execution if it detects a defined error signature. Here, the program attempts to divide by 0 inside the try block. Instead of crashing, the defense catches the 0 division error and prints a warning. The bottom finally block executes terminal commands regardless of the success or failure above. The actual work performed inside these protective structures relies on Python's foundational vocabulary, its core built-in functions, and essential keywords. Exception handling is not about ignoring errors or covering up bad coding. It is about deliberately maintaining control of the system's state when the inevitable external failure occurs. To achieve true execution safety, we must synthesize these two distinct defensive models into a single cohesive architecture for external interaction. We can achieve this by encasing an automated resource manager inside a failure interceptor. If we attempt to access a file that does not exist, a catastrophic alert is triggered from deep inside the with block. The unified architecture responds. The with statement safely seals the resource void, ensuring no memory is leaked, while the outer accept block captures the alert, keeping the overall program running. Professional coding requires accounting for the inevitable failure of external systems. Mastering Python involves building resilient, unified structures capable of handling real-world data.